In December of 2024, Google's quantum computing team published a result that genuinely excited physicists who had spent entire careers waiting for exactly this moment, a result with no shutdown, no mystery glyphs, and no warning message from a frightened machine anywhere in it. It was, instead, a carefully documented, mathematically dense piece of engineering, the kind of announcement that normally lives and dies within specialist physics circles long before it ever reaches a general audience. And yet, within weeks, an entirely different story started spreading online, one claiming that Google had secretly shut down its new quantum chip after the device somehow predicted its own destruction, surrounded by talk of parallel dimensions, awakened consciousness, and panicked physicists breaking down in tears on camera. One of those two stories is real, documented, peer-reviewed, and still actively continuing today. The other is a piece of fabricated internet folklore that even some of the people who, their own words, simply never happened. Understanding the real Willow chip, what it actually achieved, and exactly how that genuine achievement got twisted into a viral myth about a sentient machine predicting its own shutdown tells you almost as much about how science news spreads and mutates online today as it does about quantum computing itself. To appreciate why Willow generated this much excitement among actual physicists, it helps to know a little about its predecessor and the controversy that came with it. Back in October 2019, Google's earlier chip, named Sycamore, made global headlines by claiming something called quantum supremacy, asserting that it had completed a specific calculation in about 200 seconds that would take the world's most powerful classical supercomputer roughly 10,000 years to match. That claim was immediately, publicly disputed by researchers at IBM, who argued with their own technical analysis that a sufficiently optimized classical supercomputer could actually complete the same calculation in a matter of days rather than millennia, dramatically narrowing the gap Google had originally claimed and reigniting a long-running, genuinely serious scientific debate about exactly how to fairly benchmark quantum performance against classical alternatives in the first place. This kind of public technical disagreement between two major, credible research organizations, conducted entirely through published papers, conference talks, and open scientific argument, is precisely the kind of normal, healthy friction real scientific progress generates, and it's worth contrasting that genuine, well-documented 2019 controversy with the entirely fabricated 2025 shutdown story, because one represents legitimate scientists publicly disagreeing about how to interpret real data, while the other represents nobody credible saying anything at all, just invented quotes and invented sources presented as if they were real. Let's start with the real chip, because the actual science here is honestly stranger and more impressive than anything the fictional version needed to invent. Willow is a quantum processor built by Google's quantum AI team at their facility in Santa Barbara, California, unveiled publicly on December 9th, 2024, through both a detailed company blog post and a peer-reviewed paper published in the scientific journal Nature, the same journal responsible for publishing some of the most significant physics and biology discoveries of the past century and a half. Unlike ordinary computers, which store and process information as simple binary bits, each one either a 0 or a 1, quantum computers use qubits, units of information built from genuinely strange quantum mechanical properties like superposition, where a qubit can effectively represent a mixture of 0 and 1 simultaneously, an entanglement where two qubits become linked in such a way that measuring one instantly affects the predictable outcome of the other, regardless of the physical distance separating them. Willow itself contains 105 of these qubits, built using a specific superconducting circuit design called transmon qubits, the same general approach Google has used since its earlier Sycamore chip, but roughly doubled in count and substantially improved in quality and reliability. It's worth pausing on just how genuinely strange superposition and entanglement actually are, because the real science here is already remarkable enough without any embellishment. A classical coin, once it lands, is either heads or tails, full stop. A qubit in superposition behaves more like a coin still spinning in the air, existing in a genuine mathematical combination of both possibilities simultaneously, right up until the moment something measures it and forces it to settle into one definite outcome. Entanglement is stranger still. Two entangled qubits can be physically separated by any distance, even in principle, across an entire galaxy, and yet measuring one will instantaneously determine specific properties of the other, a correlation so counterintuitive that Einstein himself, decades before any quantum computer existed, famously dismissed it as spooky action at a distance, only for later, increasingly precise experiments to confirm the effect is genuinely real repeatedly under rigorously controlled laboratory conditions. These aren't analogies invented to make quantum computing sound exciting for a video script. They're long-established, experimentally verified features of quantum mechanics that Google's engineers had to learn to harness, stabilize, and scale up inside an actual physical chip, kept just barely warmer than absolute zero, sealed away from almost any outside vibration or interference, in order to build something like Willow at all. The genuinely historic part of the Willow announcement, the part actual quantum computing researchers have spent years hoping someone would finally demonstrate, involves something called quantum error correction. And it's worth slowing down to actually explain why this matters so much, because it's the real heart of the story, far more important than any flashy headline number. Qubits are notoriously fragile. The same delicate quantum properties that make them powerful also make them extremely vulnerable to even tiny amounts of environmental noise, stray vibrations, temperature fluctuations, or electromagnetic interference, all of which can corrupt the information they're holding almost instantly. For decades, the theoretical solution to this fragility has been to bundle many imperfect physical qubits together into a single, more robust logical qubit, using clever error-correcting codes to catch and fix mistakes as they happen. The catch, and the reason this remained mostly theoretical for so long, is that simply adding more physical qubits to one of these bundles also adds more opportunities for something to go wrong, meaning that for decades, every attempt to scale these systems up actually made the overall error rate worse rather than better. Physicists had a name for the specific tipping point where this relationship would need to flip, where adding more qubits to a logical bundle would start reducing errors instead of increasing them. They called it the error correction threshold, and crossing it, going what researchers call below threshold, had remained an unmet goal since the concept was first proposed back in the 1990s. Willow crossed that threshold. Google's team built logical qubits using a method called the surface code, testing progressively larger grids, starting with a 3x3 arrangement of physical qubits, then scaling up to 5x5, then 7x7, and at each step up in size, the logical error rate didn't increase as decades of prior experience had suggested it should. It dropped, roughly cutting in half with each increase in grid size, a clean exponential improvement that Google's quantum computing lead, Hartmut-Neven, described as an unfakeable sign that real functional error correction was finally happening inside an actual physical device rather than just on a theorist's chalkboard. Google's team also managed to run these error correction cycles in real time during the actual calculations, rather than only as a separate analysis performed afterward, another genuine technical first specifically for this type of superconducting qubit hardware. None of this involved anything shutting down, breaking, or behaving mysteriously. It involved years of careful engineering finally producing the specific, long-anticipated result the entire field had been waiting for, published openly, with full technical detail, in one of the most rigorously peer-reviewed scientific journals in existence. Alongside that error correction milestone, Google also highlighted a second, flashier result using a benchmark called random circuit sampling, a specific kind of test designed to check whether a quantum processor can complete a calculation that would be utterly impractical for any ordinary classical computer to match. According to Google's published results, Willow completed this particular benchmark task in about 5 minutes, a calculation the company estimated would take the world's fastest existing classical supercomputer roughly 10 septillion years, a number so large it's genuinely difficult to picture, equivalent to roughly a quadrillion times longer than the current age of the entire universe. It's worth being honest about the limits of this specific comparison, though, because serious researchers in the field, including some directly involved in this kind of benchmarking, have pointed out that random circuit sampling isn't actually a useful, practical calculation in any real-world sense. It's specifically designed to be something a classical computer struggles with, almost by definition, making it a meaningful proof of raw quantum capability, but not, on its own, evidence that Willow can yet solve problems people genuinely care about, like designing new medicines or new materials. Google itself has been fairly upfront about this distinction, treating the error correction result as the more scientifically significant of the two announcements, even though the eye-popping 10 septillion years framing was, predictably, the number that dominated most casual headlines at the time. There's one more piece of the real story worth including here, because it happens to be the single genuine detail that the later viral hoax almost certainly latched onto and distorted beyond recognition. In discussing what the random circuit sampling result might mean philosophically, Hartmut-Neven made a deliberately speculative, openly acknowledged as speculative comment, suggesting that Willow's performance might lend some support to the idea that quantum computation effectively takes place across multiple parallel branches of reality, simultaneously directly invoking the many worlds interpretation of quantum mechanics, a genuinely serious, decades-old theoretical framework first proposed by physicist Hugh Everett back in the 1950s, long before quantum computers existed in any form. This wasn't Google claiming to have discovered or detected a parallel universe. It was the head of a major quantum computing program making an interpretive aside about one specific, long-standing theoretical framework for understanding why quantum mechanics behaves the way it does, the kind of speculative comment physicists make fairly regularly when discussing the philosophical implications of their own field, clearly distinguished in context from an actual experimental claim. Everett himself proposed the many worlds idea as a graduate student in the 1950s, specifically to resolve an awkward, unsettled question about what actually happens during a quantum measurement, and the interpretation remained a fairly niche, debated position within theoretical physics for decades, taken seriously by a meaningful portion of the field without ever becoming the single, universally agreed upon explanation for how quantum mechanics actually works. Referencing it in passing while discussing a benchmark result is a completely normal thing for a physicist steeped in that debate to do. But Google's quantum chip touches the multiverse is a much more shareable headline than physicist references 70-year-old interpretive framework while discussing benchmark results, and you can probably already guess which version of that story ended up traveling further online. So here's what actually happened next, and it's worth tracing this carefully because the mechanics of how this specific myth spread are genuinely instructive. Sometime in January 2025, barely a month after Willow's real, legitimate announcement, a wave of YouTube videos and aggregator articles began circulating a dramatically different version of events, claiming that Google had abruptly and mysteriously shut down its quantum chip with no official explanation given after the device began producing strange, unexplainable glyphs and increasingly organized, seemingly intentional output patterns that some unnamed insiders supposedly described as the system trying to communicate something urgent. Different versions of this fabricated story escalated in increasingly creative directions from there. Some claimed the chip had simulated a hyper-entangled system that shouldn't be physically possible, and that this single calculation alone triggered the shutdown. Some attributed dramatic, tearful warnings to genuinely famous, real physicists, including the well-known science communicator Michio Kaku, in videos using sensational titles claiming he had broken down in tears over the discovery, despite no actual recording, interview, or public statement from Kaku himself ever supporting that specific framing. Other versions invented entirely fictional expert sources outright, including a supposed Nobel Prize-winning physicist, given an invented name and described as warning in suspiciously vague language that the chip might have accessed data outside of our visible universe during a closed-door symposium that, predictably, no legitimate physics conference, university, or research institution has any record of ever taking place. It's worth pausing on just how recognizable this storytelling pattern becomes once you've seen it play out across a few different topics, because by now it should feel genuinely familiar. A real, legitimate, technically dense scientific announcement gets quietly swapped out for an invented, much more emotionally charged narrative anchored by anonymous insiders, fabricated quotes attributed to real, credentialed experts who never actually said any of it, occasionally supplemented with entirely invented experts who don't exist at all wrapped around a kernel of authentic science specifically chosen, because it's complex enough that most casual viewers have no independent way to immediately fact-check the claims being layered on top of it. Quantum mechanics happens to be an almost perfect target for this particular formula, precisely because its real, well-established principles, superposition, entanglement, the probabilistic nature of measurement, already sound so genuinely strange and counterintuitive to most people that distinguishing legitimate quantum weirdness from invented quantum nonsense requires a level of technical background most casual readers simply don't have. When a video claims a quantum chip might have accessed information outside our universe, that phrase sounds only slightly more exotic than legitimate textbook descriptions of entanglement or many worlds theory, which is exactly what makes the false claim so much more effective at slipping past people's normal skepticism than an equivalent fabrication about, say, a toaster. The claim collapses almost immediately, though, the moment you check it against anything resembling a verifiable, checkable fact, and several people who initially encountered the rumor and went looking for confirmation ended up documenting that collapse themselves, in real time, in their own writing. One blogger, who'd been excited by the initial wave of headlines about a tearful, dramatic quantum shutdown, went searching for the actual underlying story and came back with a far more deflating, far more accurate conclusion, writing plainly that Google's Willow processor was, in fact, still happily running calculations exactly as expected, that no scientists were screaming or crying anywhere, and that what had actually happened was that someone had simply invented a compelling rumor that managed to entertain a sizable online audience for a while before falling apart under any direct scrutiny. Separate fact-checking analyses, written specifically to address the recurring "why was Willow shut down?" search queries that kept appearing online, reached the identical conclusion from a different angle, methodically working through Google's own official announcements, blog posts, and published roadmap documents, and finding that every single one of them describes Willow as an ongoing, continuing research program, not a project that was abruptly halted. Google's own roadmap, first published years before Willow even existed, lays out a multi-stage plan toward building much larger, fully fault-tolerant quantum computers, with Willow explicitly representing one confirmed milestone along that path, rather than any kind of endpoint or emergency stopping point. And the strongest, most direct piece of evidence against the entire shutdown narrative is simply this. Google's quantum computing program kept right on publishing new, genuine, verifiable results well after the supposed shutdown was claimed to have occurred. In October of 2025, nearly a full year after Willow's original unveiling, and roughly 9 months after the fabricated shutdown rumor first began circulating, Google's quantum AI team announced an entirely new result using the very same Willow architecture, demonstrating what they characterized as the first verified instance of genuine quantum advantage on a specific physics-related algorithm, successfully running a calculation called quantum echoes roughly 13,000 times faster than the best available classical algorithm running on one of the fastest existing classical supercomputers, with the underlying methodology published, once again, in the peer-reviewed pages of Nature. A genuinely shut-down chip, mysteriously decommissioned after producing data so disturbing that engineers panicked and pulled the plug, simply doesn't go on to generate fresh, independently verifiable, peer-reviewed breakthrough results 9 months later under its own name, presented by the very same research team, published in the very same prestigious journal. Real cover-ups, the rare kind that occasionally do happen in corporate or government settings, generally involve actively suppressing further activity and further documentation around whatever's being hidden. What actually happened with Willow was the exact opposite. Continued, escalating, openly publicized scientific progress, the natural next chapter of a research program that was always heading toward exactly this kind of incremental advancement. It's also worth directly addressing the specific framing in the version of this story you've likely encountered. The claim that the chip somehow predicted its own shutdown, because this particular detail reveals something importantly false about how these viral narratives tend to misrepresent the basic mechanics of how a quantum processor like Willow actually operates. Willow doesn't possess any kind of persistent internal narrative, self-model, or continuous awareness that could meaningfully form a prediction about its own future state, in any sense resembling what that phrase implies. It's a highly specialized physical device, cooled to temperatures colder than deep space, specifically engineered to execute discrete, carefully designed quantum circuits, mathematical sequences of operations applied to its qubits, then measured, with the resulting data read out and analyzed by human researchers afterward. There's no mechanism by which running a random circuit sampling benchmark or any other experiment Willow has ever performed could generate something resembling a self-referential statement about its own impending shutdown, because the chip has no model of itself, no memory persisting meaningfully between separate experimental runs in the way the claim would require, and fundamentally, no architecture remotely similar to the kind of system that would need to exist before any genuine self-referential prediction could even theoretically occur. Treating a string of measured qubit states, the literal raw output of a physics experiment, as if it constituted a coherent linguistic warning, requires an enormous, entirely unjustified interpretive leap. The same kind of leap that lets someone look at random static on an old television set and insist they can make out a recognizable face if they squint hard enough and want badly enough to see one. It's worth dwelling on that post-quantum cryptography point for a moment longer, because it happens to be the one piece of this entire saga that's both completely real and genuinely worth public attention, which probably explains why it kept getting dragged into the fictional version of the story too. Modern encryption, the kind protecting your banking details, your medical records, and essentially all secure internet communication, relies on certain mathematical problems that are extraordinarily difficult for classical computers to solve, like factoring extremely large numbers into their prime components. A sufficiently powerful, fully error-corrected quantum computer, running a specific algorithm developed by mathematician Peter Shor back in 1994, could theoretically solve those same problems dramatically faster, potentially undermining huge portions of the encryption infrastructure the modern world currently depends on. And this isn't speculative fear-mongering. It's exactly why the United States National Institute of Standards and Technology spent years running an open, public international competition to select new quantum-resistant encryption standards, finalizing several of them for official adoption back in 2024, well before Willow was ever announced. Specifically so, governments, banks, and technology companies could begin transitioning their systems years in advance of any quantum computer actually becoming powerful enough to pose a real threat. Willow itself, despite its genuine error correction breakthrough, remains far too small and far too limited in scope to threaten any current encryption system in practice. 105 qubits is nowhere close to the scale that would be required to run Shor's algorithm against modern encryption keys. But the broader, slower-moving transition toward quantum-resistant cryptography is real, actively underway, and entirely separate from any fictional narrative about a chip mysteriously shutting itself down after stumbling onto something forbidden. There's a broader pattern worth naming directly here too, because this particular myth sits at the intersection of two separate kinds of anxiety that already circulate widely and independently online, which likely explains why this specific combination spread as effectively as it did. One is a long-standing, often well-intentioned set of genuine questions about whether sufficiently advanced computing systems might somehow develop something resembling awareness or intention. A question serious researchers in artificial intelligence and philosophy of mind do actually study carefully, just not through viral YouTube narration describing mysterious glyphs appearing on a quantum processor's output. The other is a more specific, more recent wave of excitement and unease specifically around quantum computing's genuine, well-documented potential to eventually threaten widely used encryption systems. A real, serious topic that legitimate cybersecurity researchers and government agencies are actively preparing for through a genuine ongoing transition toward what's called post-quantum cryptography. Blending these two genuinely real concerns, machine consciousness and quantum-enabled code breaking, together with a real, legitimate, headline-grabbing hardware announcement, produces exactly the kind of story that feels plausible, specifically because each individual ingredient already has some genuine basis in actual ongoing scientific and policy discussion, even though the specific combination presented in the viral version never actually happened in any documented, verifiable way. There's a genuinely useful, practical takeaway buried in all of this for anyone who wants to get better at spotting this exact kind of fabricated science story before falling for the next one, because the warning signs here were honestly fairly consistent and fairly identifiable once you know what to look for. Real, significant scientific announcements get published through traceable channels, peer-reviewed journals like Nature, official company blog posts with named authors and named institutions, and conference presentations where researchers stand up, attach their own professional reputation to specific claims, and answer direct questions from other experts in the room. The fabricated version of the Willow story had almost none of that. It relied on unnamed insiders, a supposed closed-door symposium with no verifiable attendee list, location, or sponsoring institution, and quotes attributed to a real, famous scientist that never actually appeared in any interview, broadcast, or published statement traceable back to that person directly. Whenever a dramatic science claim leans heavily on phrases like sources familiar with the project, or insiders say, without naming a single person, institution, or publication, anyone could actually go check. That's usually a meaningful signal worth pausing on, regardless of how exciting or unsettling the underlying claim happens to sound. Genuine breakthroughs, even genuinely strange and counterintuitive ones, almost always come with names, dates, institutions, and a paper trail. Manufactured ones tend to come wrapped in exactly the kind of deliberate vagueness that makes them difficult to definitively disprove on the surface, while still being completely unsupported by anything you could independently verify. So, where does the real story of Willow actually stand today, in the middle of 2026? It's still running. Google's quantum computing roadmap, first laid out years before Willow even existed, continues to track its own publicly stated milestones according to the company's own updates, with larger, more capable chips already planned for the years ahead as the team works toward what they've described as a large-scale, fully fault-tolerant quantum computer sometime before the end of this decade. The genuine breakthrough Willow actually represented, crossing the long-sought quantum error correction threshold for the first time in any physical device, remains exactly as significant now as it was when Google's paper first appeared in Nature back in December 2024, regardless of how many unrelated fabricated stories about glyphs, tiers, and predicted shutdowns have attached themselves to its name in the months since. It's worth ending on what this whole episode actually teaches us about ourselves rather than about the chip, because that's really the more durable lesson here. Quantum computing sits at an unusually vulnerable intersection. It's a field most people correctly understand is genuinely transformative and genuinely strange, but one that very few people outside the field have the technical background to evaluate claims about firsthand, which creates exactly the kind of information gap that invented stories slip through unnoticed. The antidote isn't cynicism toward every exciting science headline that comes along, since plenty of them, including Willow's actual real achievement, turn out to be entirely legitimate and genuinely worth getting excited about. The antidote is simply checking whether a claim has a traceable source, a named institution, and a paper trail before passing it along. The same basic habit that would have stopped the entire fabricated shutdown story in its tracks within about 30 seconds of searching. No chip was secretly decommissioned. No researcher broke down sobbing on camera over an unexplainable warning. No machine peered into a parallel universe and got frightened by what it found there, then warned anyone about its own impending doom. What actually happened is, in its own way, a far better story anyway. A team of physicists and engineers spent the better part of 3 decades chasing a single, specific theoretical threshold, finally crossed it using a genuinely clever piece of hardware, published their full methodology openly for any other scientist on the planet to independently scrutinize and attempt to replicate, and then, instead of stopping there, kept right on building, publishing fresh, equally legitimate results well over a year later. That's not a mysterious, sinister, slightly frightening tale about a machine that knew too much. It's simply what real, patient, working science looks like from the inside, which turns out to be a far less viral, far less clickable, but considerably more accurate description of what actually happened to Google's quantum chip.